Thank you very much. I'm really delighted to speak to this crowd again. Actually, I think I gave a talk on very broadly the same kind of subject in the ancient times, infinity times before the pandemic. And so I'm actually very happy to be able to talk about a completely complementary aspect of the story today. This is really broadly a line of work. Oh, what am I doing? Broadly a line of work that I've been pursuing with a large number of wonderful physicists and mathematicians over the past decade or so. There will be essentially no references in this talk, but I will highlight that some of the things that I'm talking about that are really what's occupied me and my collaborators more than anything else over the course of the pandemic is work in very much in progress with the mathematicians Hugh Thomas and Pierre-Yves Plamondon, and two wonderful young physicists, Giulio Salvatore and Hadley Frost. We all know that the ability to talk about laws of physics compatible with the symmetries of space-time and quantum mechanics are united in the general theoretical framework of quantum field theory. And that's why it's especially dramatic that there are storm clouds now early in the 21st century that are associated at least with one, maybe even both of these principles. It's very likely that space-time is an approximate concept. More fundamental description of physics will remove it because of well-known issues having to do with gravity and quantum mechanics. Maybe even extensions of quantum mechanics will be needed for very deep questions about cosmology, not stupid things about modifying quantum mechanics in some Stern-Gerlach experiment. But it's conceivable that some extension of quantum mechanics will be needed to figure out how to apply quantum mechanics or an extension of it to the entire universe. And by far the most fertile place for all this activity to be explored, for these questions to be explored over the past 20 years, has been in the context of theories in the sort of tin can universe of empty de Sitter space, where if you imagine that you lived in empty de Sitter space, the kinds of quantum mechanical observables you're allowed to talk about are anchored to the walls of this tin can at infinity. You can imagine pinging the walls, waves go in, crash into each other, and come back out. The results of the experiment start and end on the walls. And the amazing thing is that there's a theory that only lives on the walls in one lower dimension, the theory of quantum mechanics. The strong dynamics, out of the strong dynamics of which emerges the extra dimension of space, other dimensions of space, gravity, strings, all sorts of other things. I'll be talking today about an even more familiar set of boundary observables. In a sense, the kind of first place where the realization that boundary observables were all you're allowed to talk about when you have quantum mechanics and gravity really came in the context of scattering processes in ordinary flat spacetime. Now, our spacetime is not flat, it's asymptotically cosmological, but it's to an extremely good approximation flat. And the observables that we can imagine measuring in principle with infinite accuracy, even with quantum mechanics and gravity, in an asymptotically flat space-time, involves scattering particles from infinity, having them bang into each other and going back out to infinity. These are the analog of the boundary correlation functions in empty de Sitter space, now in flat space. And these are objects that are much closer to home. We measure these things. They're of central importance to the experimental program of high-energy physics. Okay, so those are the two importances of these objects. A, they're the analog of the boundary observables in asymptotically flat space, which is one significant step closer to the real world. And B, we actually care about them in the real world directly. And that's what makes it, if we now think about just the practicalities of how we go about thinking about these amplitudes, if you want to extract, if you want to talk about observations at the Large Hadron Collider and extract interesting potential hints of new physics over the background from ordinary processes, you have to learn how to calculate ordinary standard model processes to high precision to look for the needle in the haystack. And that requires you to calculate things like the amplitude for two gluons inside the protons banging into each other, and have not just two come out, which is what you put on a problem set for graduate students, but three come out or four come out, or more complicated things happen. And these need to be understood with pretty good accuracy because these are the sort of numbers that are involved. You know, there's billions of collisions a second, but we're maybe looking for things that might be produced once every minute or so. So we have to understand these backgrounds very well. Now, in principle, this just looks like an engineering problem. After all, Feynman taught us long ago how to think about all these processes. This is not exotic physics. It's not new physics. It's completely standard textbook physics. We draw all these Feynman diagrams. At leading order, we just draw diagrams without any closed loops in them. These are called tree diagrams. More generally, there could be diagrams that have closed loops in them. And for this process with 2 gluons in and 4 gluons out, well, there's just a combinatorial explosion in the number of possibilities. And no one guarantees that the answer to a complicated seeming question should be simple. But also physics is a great way of rewarding morally good behavior. And the people who actually had to do these calculations, because the experimentalists needed the answer, a little over 30 years ago, discovered something astonishing. First of all, if you just do it by the standard textbook method, you get 100 pages of crap. Okay? So no one guarantees that it looks, the answer looks easy. But these people discovered a little over 30 years ago that in some favorable cases, when the helicities of these gluons are especially simple, those hundreds of pages collapse to a single term. Okay. And I won't define what these objects mean. Just want you to see that it's possible to write the whole answer on just as one term. And these objects are roughly the square roots of dot products of Lorentz invariant dot products of momentum. This makes it clear that Feynman's way of thinking about this physics, the standard formalism of quantum field theory, whose purpose in life is to make the usual rules of space-time and quantum mechanics manifest, is clearly hiding something else. It's hiding the fact that the answer is incredibly simple. And so that's an invitation to try to think about this completely bread and butter physics from a new perspective that explains where the simplicity comes from. So there's, back then, 30 years ago, it was not obvious this was the tip of a giant iceberg. Today, we know it's a tip of a very, very big iceberg. And so it's an invitation to think about the standard physics in a totally different way. The idea being that in this totally different way, we will not see the usual principles of space-time and quantum mechanics so manifest. If we do that, we're back to the picture of particle trajectories in space-time, meeting at points in space-time, interacting at points in space-time, and adding up every way that it could happen in order to be compatible with the sort of path integral picture of quantum mechanics. Instead, what we want to do is find a different question. You know, you're some experimentalist far away at infinity. We'll return to this imagined experimentalist a number of times in this talk. You just see this pattern of amplitudes, and you want to know what gave rise to that pattern. Well, one answer for what gives rise to it is to imagine integrating into this picture the interior of the space-time and all these particle trajectories and all this, all the different ways that this could happen. That's the standard answer. That's a standard question to which the amplitude is the answer, is local unitary evolution in space-time. But what we want to do is find a different question. We want to find a different question that naturally lives in the space of the data associated with this problem, does not invoke the interior of the space-time or something like a Hilbert space in any way. We want to find a different question that gives us the same answer, and then hopefully see and maybe expose these remarkable hidden structures, and hopefully see how this something else gives rise to the properties of amplitudes that we ordinarily ascribe to the presence of space-time and quantum mechanics. The underlying vision and hope being that there's really some other structure there, perhaps more abstract, involving more alien ideas. But once we understand it, we'll see how, when interpreted properly, we can think of it as giving rise to phenomenon that live in space-time and are compatible with the principles of quantum mechanics. So if such a vision can be realized, if there is some deeper structure underlying space-time and quantum mechanics, it's clear that it has to involve ideas that are both new physical ideas and new mathematical ideas. And let me begin with at least a cartoon of what the sort of basic physical idea is. So one of the things that you get used to very early on when you think about the usual formalism of quantum field theory is this a dichotomy between on-shell and off-shell. When you have an ordinary particle moving along, it has some form momentum and energy and momenta. P squared is equal to m squared. So there's a restriction that the energy squared minus the momentum squared is equal to m squared, and we say that that puts the form momenta on the mass shell. This is a hyperboloid. This hyperboloid is called the mass shell, so we call this on the mass shell. On the other hand, when we think about interactions between particles, for example, something like the Coulomb law or the Yukawa law for massive particles, well, we know that in position space, non-relativistically, there's a 1/r potential. its Fourier transform in momentum space is 1 over q squared. And that is generalized in a relativistic theory to something like 1 over p squared, where p squared is a relativistic momentum. So we have all these propagators that look like 1 over p squared minus m squared. And it's extremely important that in these intermediate lines in all these pictures that the p squared is not equal to m squared. Amongst other things, if it was equal to m squared, everything would be infinity everywhere. Okay? So we must have all of these off-shell lines in our description of the physics and the standard way of thinking about it. So this is, again, the dichotomy between real and virtual particles. Real particles propagate from infinity or out to infinity, but the virtual particles are all these things that propagate over finite distances in the middle of these Feynman diagrams, and they're sort of a convenient fiction that's needed to manifest the standard rules of locality and unitarity. And it's totally manifest that it's the virtual particles that are responsible for all of the horrible complexity that I was telling you about earlier. It's really the fact that you're dragging around all these virtual particles, even though they're not there in the actual observable that you're talking about. So at least one aspect of the physical idea is to eliminate the notion of virtual particles. Never talk about virtual particles. If we don't talk about virtual particles, they're very important to give us this sort of local unitary description of the physics. So if we don't talk about virtual particles, how can we decide whether if someone hands you some function and claims it's the amplitude, how can we decide whether it's legal? How can we decide whether it comes from reasonable physics or not? And in greatest generality, we still don't know the answer to this question, but we definitely know the answer in many simple cases. So let me just tell you what's going on in these very, very simplest cases that would correspond to tree processes. So imagine you have this process, okay? So some basic process, 4-particle scattering, which is mediated by some intermediate particle of mass m. Well, here we can clearly have a resonance when p1 plus p2 squared equals m squared, okay? And the amplitude has that divergence that we talked about. That's the sort of classic resonance, the same as for the ordinary harmonic oscillator. So the amplitude has a pole when the virtual particle becomes real. And one aspect of locality is where these poles are. The poles are when a sum of the subset of the momenta go on shell. They look like 1 over p squared minus m squared. They don't look like 1 over p squared 2 squared minus r squared t squared. They look like these very simple things that are just poles in sums of the external momenta. So that locality has a fingerprint on the amplitude, is where the poles are. And unitarity also has a fingerprint. It tells us that in the neighborhood of that pole, the amplitude has to factorize. It has to have an interpretation. We got the pole because this intermediate particle went from being virtual to being real. So we have to interpret this amplitude after we strip off this divergent pole as being interpreted as the amplitude to produce this intermediate particle that then propagates a long distance. That's what's responsible for the pole, for it to decay on the other side to 3 and 4. Okay, so the rules of space-time and quantum mechanics are then reflected in a very concrete way in this function, right? There's some function of the momenta, rather simple function for these tree amplitudes that only has poles, nothing more complicated than poles, but the rules are reflected in a very simple way. Locality says that the only poles happen when this particular sum of the subset of the external momenta goes on shell, and unitarity tells us that the amplitude doesn't factorize on the poles in that way. Yes?
So if you go back, this is a property of tree diagram.
So far, I'm just talking about tree.
So where is the quantum mechanics and the unitarity and all that?
Well, because we're still talking about an amplitude, and so this is still interpreted as an amplitude, and the formula S dagger S equals 1 is still meaningful even at tree level. Okay, so the imaginary part of the amplitude is coming from the I epsilon that I've suppressed in these propagators, and in order for the imaginary part of the amplitude to correctly give you the optical theorem, you have to have this factorization. Thank you. All right, so all of this gives us now a more concrete strategy for this sort of vague question that I started with. Is there a different question to which the amplitude is the answer? And now the more concrete strategy is to find this different question. What is the purpose in life of this different question? To find a different question that's formulated directly in the kinematical space of the sort of on-shell momenta of the scattering process, to which this function A P1 through Pn is the answer without referring to the interior of the space-time or thinking about Selfcontained diagrams or anything like that. Okay. But which nonetheless gives correct poles and correct factorization. So that's really the sort of program that we've been embarking on for the past decade or so. And so the nature, so something is starting to emerge in this 10, 11, 12 years of work. The emerging picture is that when you go to this kinematical space, at first it seems like a completely boring, arid, and dry place. What is the kinematics that the amplitude depends on? N null momenta, or dot products between pairs of n null momenta, or other ways of talking about this kinematic space. But it doesn't seem to be a familiar place with anything interesting that you can do there. But there is something, there is interesting kinds of questions to ask there that involve, to begin with, combinatorial ideas that are then lifted to certain geometric ideas known as positive geometries, that are then associated with the analytic ideas, certain differential forms that have singularities on these geometries, which is what the amplitudes end up being associated. This story began with gluon scattering amplitudes and their maximally supersymmetric cousins. And there, the role of this, the word associated with this series of ideas is the amplituhedron. And around 4 years ago, we started seeing this in the context of the very simplest possible scattering processes, just for spin zero particles, just for scalars in any number of dimensions, no supersymmetry. And that's really what I'll be telling you about today. There are analogs of these ideas at a very primitive level that are starting to be seen in cosmology. And what I find exciting about this subject is that it describes real world physics in a reasonable approximation, and it exposes hidden things, hidden symmetries, and some beautiful new mathematical structures associated with the stuff that describes the world we see when we look out the window. And it's just pure magic in physics right under our noses. Now, I've learned the hard way in trying to give talks about this subject that it's impossible to, in a reasonable time, even by my standards, in a reasonable time, really give a completely coherent introduction to all of the ideas involved. It's definitely not impossible, but it will take 5 or 6 hours and not 1 or 2 hours, or 1.5 hours. So what I want to do in this talk is something else. Is give you a few self-contained vignettes, okay? Just some sort of pictures of what some of the ideas are and the kinds of the kinds of pictures and thoughts that are involved in this business. And so there'll be sort of 3 vignettes, and they'll have the property that each one of them will have something that if you care at all, you can go home and play with it on a piece of paper yourself, solve some equations yourself, and just play around and see that they do something interesting. If it's not clear to you that there's a coherent large structure that connects all of them, all I can do is promise you there is a coherent large structure that connects all of them, although we don't understand it entirely yet. So, but anyway, without apology, I'm just going to give a few self-contained videos. Okay, so let's begin with this. But just to say one thing, since I think there are some. It's a broad audience, so maybe this will mean something. Subsets of this paragraph will mean things to different people. I should say that the sort of conceptual framework underlying these ideas is associated with a number of new mathematical structures in a variety of parts of mathematics that are now that talk to each other in an interesting way. So there's structures in combinatorics and algebra and geometry that go from notions of total positivity, extensions of ideas of cluster algebras and cluster varieties, tropical geometry and hyperbolic tropical geometry, right? What's happening here? And perhaps most fundamentally of all, the representation theory of the category of Quiver representations. All right. So let's start with the first invitation. This is how an experimentalist, a very simple-minded person would start running into the kinds of ideas that I'm about to see. So we're going to talk about the simplest possible theory of scalars like Higgs's. And so the diagrams that we're going to draw, for the moment, I'm going to focus just on drawing tree diagrams. So the basic interaction is the cubic interaction, but we're also only going to draw planar diagrams. Okay, so this is for simplicity, this is, you could think of this as coming from an underlying theory with a scalar phi in the adjoint representation, or an n by n representation of a UN global symmetry, and a trace phi cubed interaction, in which case we're using the usual 't Hooft expansion. If those words don't mean something to you, just imagine drawing diagrams which are just with cubic vertices, but where the external labels are cyclically ordered in the way that I've drawn. So at 4 points, I'd have these two diagrams. At 6 points, I'd have different shaped diagrams. I have this kind of diagram plus cyclic friends. I have this Mercedes-Benz diagram with cyclic friends and so on. Now, a feature of these tree amplitudes and of the ordering, which is that the only poles that you see here, for example, in this example, the only poles that you see are like P1 plus P2 squared or P2 plus P3 squared. The only poles you see here are P1 plus P2 squared or P1 plus P2 plus P3 squared, which is equal to P4 plus P5 plus P6 squared, but momentum conservation on the other stuff. So these are the only poles that can make an appearance involve a sum of consecutive momenta, Pi plus Pi plus 1 dot dot up to Pj minus 1 squared. And it's convenient to represent them graphically in the following way. Since we have momentum conservation, all the momenta add up to 0. So when we draw the momenta end to end on a piece of paper, we get this picture of a closed polygon. And you see that if I take the length squared between 2 points here, that length squared is exactly equal to one of these planar poles. Okay, so all the variables that are going to show up, all the Lorentz invariants that show up in this problem can be associated with chords of this n-gon. That n-gon captures the kinematics, and the chords of the n-gon capture all the variables. In fact, the chords of the n-gon give you the correct number of variables to be a basis for all the possible dot products that you can build out of the momenta. So it's just a particularly convenient way of representing them. All right, so now imagine that there we're cheating looking at Feynman diagrams. Imagine that you're an experimentalist, and all the experimentalist has is their fingers on the dial of the momenta. They can dial the momenta around all they like. What would they notice? Well, they would probably notice that the amplitude has poles when a sum of the momenta squared go on shell. That's probably the first interesting thing they would note, is that the amplitude blows up somewhere. And then what they'll do depends on the kind of experimentalist they are. And especially experimental particle physicists, anyone who knows them knows that there are two varieties: those who wanted to be theorists and those who didn't. Okay? So those who wanted to be theorists would know there's something important about poles. They should look at the residues of the poles. So they do very accurate measurements in the neighborhood of these poles, and they would discover, amazingly, that the amplitude factorizes into the product of two lower things that they saw. So that's what they would be most excited about, is that there's a picture of factorization. So they would go to a conference and say, these things that I'm measuring, I don't know where they come from, but they have this great property that when a subset of the momenta goes on shell, the result, after you strip off the thing that's blowing up, factorizes into the product of two lower things. And then the theorists in the audience, depending on whether the name is Feynman or Deligne and Mumford, will have different reactions to this. Okay? If their name is Feynman, they'd say, oh, I know what's going on. What's going on is that these amplitudes are coming from pictures like this with all these virtual particles in the middle. And this picture makes it manifest that those are where the poles are, and then it factorizes all the poles. So that's the explanation of what's happening. The mathematician could say, no, I've seen this before. This structure that you have some space and a singularity or a boundary of the space is the product of two lower spaces like that. Well, that's exactly what happens in the simplest moduli space of all. N points in P1, n ordered points on the boundary of a disk also has exactly this property. So you see, these are sort of two pictures for explaining where factorization comes from. One of these pictures is associated with the particles in space-time, and the second picture is associated with the string worldsheet. Okay, so these are sort of two basic facts that give you factorization from a sort of more primitive place, and which we can then interpret in some way as giving us the amplitudes that factorize in the way that they should. All right, so factorization is the star of the show. We have the picture of particles in space-time or of the string worldsheet. But the hero of this part of the story is a lazy but smart experimentalist who doesn't really care to make detailed measurements, but is excited about the fact the amplitude blows up and says, oh, it only blows up when P1 plus P2 squared goes to m squared. can I make it blow up more? Having made it blow up once, can I now sit on that pole and tune the other dials to make it blow up more? And here they'll discover at 4 points that they can't. It only blows up when P1 plus P2 squared goes to M squared, or when P2 plus P3 squared goes to M squared, but not both. That's again secretly for drawing diagrams, because there's no diagram that has both channels, and it's both this channel and the other channel. But they don't know it's coming from diagrams. They just notice that they only get one pole and not the other one. But at 5 points, for example, they notice there's an interesting pattern to how it can blow up. That it can blow up when P1 plus P2 squared goes to M squared, and then when P1 plus P2 plus P3 squared goes to M squared, but not in a random way. Not when, let's say, P1 plus P2 squared goes to M squared and P2 plus P3 plus P4 squared goes to M squared. That one is not there. So there's some interesting pattern in how the poles come together. So if we draw this in the language, instead of these P1 plus P2 plus P3s, in the language of these X variables that I talked about, the chords on the n-gon, we see that we're allowed to have P1 plus P2 squared would be this purple chord, that we can have a pole associated with the purple chord and one associated with the blue chord, but not both of them. If I go to 5 points, I can have a pole associated with this blue chord and one associated with this purple chord, but not with a different purple chord that crosses the blue one. So the physics of locality is encoded in a very simple pattern of which kind of poles can come together. And the kind of poles that can come together correspond to chords that do not cross in this So just to say again, locality and unitarity in this language, what is locality? Here's a pattern of allowed poles that can come together. Here's a maximal pattern of 3 poles in this example that can come together. But here's something that cannot. Okay, so the crossing chords are not allowed, and that's locality. Now, what is unitarity? In the neighborhood of this pole, when some xij goes to 0, the residue on the pole is just factorizes into the product of the amplitude that you get just by cutting this surface over. Okay, so locality and unitarity are just translated to these very simple facts in this picture. And now comes the interesting point that this experimentalist might notice, that if they wanted to summarize the pattern of how the poles can come together, it's actually captured by a shape. Okay? For instance, in the case of 5-particle scattering, which looks a little bit more non-trivial, what they would do is say, okay, here's my single pole that I could have. Now, what are the double poles that I could have? Well, I can draw another line here that doesn't cross this one. So I can draw it on that side, or I can draw it on that side. So it's natural to think of this as an edge of something, and having 2 of them would correspond to vertices. And you see from here, I can think that there was another single pole that I could have on this side, and the two double poles that I could have are arranged like so. Okay, so the whole picture goes around. Quite coincidentally, it turns out that you get something that looks like a pentagon again. But there's something slightly interesting which has happened, which is that the pattern of how the poles come together is captured by the facets of a simple geometric shape. Okay, so you can think of the interior as being no poles at all, one pole being the codimension 1 faces, just the edges, 2 poles being the complete triangulations. The analog of this for 4 points is even simpler. I just have an interval, and the 2 sides are the 2 triangulations of the square. Well, this continues to be true at higher points, and now the shape looks more interesting. So this is what the shape looks like for 6-point scattering. This is a famous shape known as the associahedron, or the Stache Polytope. It was discovered in the 1960s. And the interesting thing about it is that you can fill this, it's a 3-dimensional shape that reflects the fact that for this problem with 6 points, I can put up to 3, I can have up to 3 poles. And every face of this picture is associated with just 1 chord. Every edge is associated with 2 chords, and every vertex is associated with 3 chords that can come together in a non-overlapping. What's non-trivial and not at all obvious ahead of time is that this pattern of how the poles come together should be captured by this geometric shape at all. If there's any geometric shape associated with it, is non-obvious a priori. Okay, so that's, but furthermore, this picture actually knows everything that our smart experimentalists knew as well. because this picture also knows about factorization. Okay, so in other words, when we knew about factorization, we didn't know that this pattern of poles comes together in this shape. We've known about factorization, from school since for 60, 70 years. But the fact that the pattern of poles comes into a shape is not obvious from that. Nonetheless, if you see this shape, factorization is obvious. And the reason is that there's something remarkable about this shape. When you go to its facets look like direct products of exactly the same kind of shape in a way that perfectly reflects factorization. So for instance, this object, if you look at it closely, has 6 pentagonal faces and 3 square faces. And each pentagonal face you really think of as the product of the geometry associated with a 5-particle scattering, this kind of factorization channel, and that of the 3-particle scattering, which I didn't even bother writing because it's just a point. But the 3 square faces are associated with this factorization into 4 particles on one side and 4 on the other. Remember, the geometry for 4 points was just an interval. So the fact that there is a square is simply that an interval across an interval gives you a square. So the particle in the string picture don't make this obvious, but the associahedron does see everything. Okay? It does see everything since its facet structure of this remarkable factorization problem. And so one motivation behind our work of the past number of years is how can we make it obvious? In other words, how can we make it obvious that the pattern of poles is associated with a geometric shape? How can we make it obvious that it's associated with a polytope, which has the property that it factorizes on its boundaries? So we want to make this fact as obvious as possible. And we want to make this obvious by asking an interesting question in the kinematic space where the amplitude is defined. Now, around 4 years ago, we actually ran into an interesting realization of the associahedron. The picture that I drew before was just a kind of a combinatorial picture, but it makes it clear that there's an object. It's a polytope. That means it's cut out by inequalities. Okay, so it has flat faces. It's cut out by a bunch of linear inequalities. But you can draw it in many, many ways. Well, we ran into a very particular realization of the associahedron. So if you look carefully, it has the same sort of combinatorics. The shape is the same structure as before. It has 6 pentagonal faces, square faces, 3 square faces that meet in the same ways. But it's a very particular looking shape. If you look carefully, there's a lot of parallel sides in this shape and so on. I won't say more about this because we'll understand where this comes from a little more in a moment. But this seemed to be even more sort of directly, closely associated with the amplitude. So we wanted to know how this particular realization of the associahedra, how we could make them obvious. All right, so that's the invitation. And now let me move on to telling you about what some of the sort of central ideas are. Again, one of the vignettes involving positivity polytopes and particles. So what I want to do is tell you explicitly how to get these shapes. Where these particular kind of shapes come from. Let's just back up for a second and how we get them from asking some questions in the kinematic space. Now remember, what is our kinematic space for this problem? We're still just talking about the simple tree amplitude. What is our kinematic space for this problem? It's just the space of all the chords of this n-gon, right? So to begin with, we're just going to list all the chords of the n-gon, right? How are we going to list them? Well, the problem obviously has a natural cyclic symmetry. So we're going to list them by starting from one of them, let's say 1, 2. Now remember, the edges of this polygon, they correspond to the momenta that are just the external particles, and their p squared is equal to m squared. Okay, so we don't care about, or 0. We set them to any value we like. They're not variables. Okay, so that's why they're denoted in black here. But I start with 1, 2, and then I just translate the indices in the obvious way. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. This happens to be 7 particle scattering, so I stop at 1, 7. Okay, so I'm just drawing them on a grid. Why am I orienting them like that? No deep reason. It just makes it a little more evocative, the picture that we want to say here. But that's all we're doing. We're just drawing we're recording all the variables in this strip. You'll notice that if I have the variable ij here as some sort of point xt, if you imagine this in a continuum picture, then ji would be 1 minus x, 1 plus t. So sort of translate up this script in this way. So it has a Mobius identification because ij and ji correspond to exactly the same chord. And one of the sort of interesting things about this picture of simply recording the positions, recording the variables, is that there's a very simple characterization of whether two chords cross. If you give me a chord ij and a chord kl, clearly it's important whether they cross or not. But in this picture, if I now just give this direction the name time, this direction the name space, whether the chords cross or not has a very nice interpretation. Chords cross if ij and kl are the past and the future corners of a causal diamond that fits inside this kinematic spacetime. Okay, so that's a nicer way of capturing this fact. Now, I gave you a list of all the variables, but again, because ij is equal to ji, this is a very redundant list. So we're just going to pick out some wedge out of this infinite picture that gives me all the variables once and only once. Okay, so this is one particular wedge. And so you see I'm including 1, 3 here, but not 3, 1. So every one of the variables occurs once and only once. You can do it any way you like. This is a simple way of doing it, so let's stick with that. So in other words, this is now our kinematic space. Okay, so our kinematic space is just the set of all the variables in this right triangle, right? Now we have to do something here. And so this is what we're going to do. Now we're going to ask a question in this kinematic space. And the answer to this question is going to give us all the objects that we're talking about. What is the question? So our variables are xij. Again, these consecutive guys, I plus 1, are set to a constant, let's say 0. But this is where the word positivity comes in. So we're going to ask that all these xij's are positive, or greater than or equal to 0. Now, that's the first demand. The second demand is that we're going to impose a relation between all these xij's for every little mesh in this picture. In other words, we're really going to take this picture of kind of a local, this looks like a kind of a local space-time, right? I mean, the way I call this time and space, this kind of looks like a space-time grid. We're going to take the picture of some kind of locality in this kinematic space-time, quote unquote, seriously. And what we're going to do is write down an equation of motion, which is just the lattice analog of the wave equation. Okay, so the lattice analog of the wave equation, it just says past plus future minus left minus right is equal to the source. It's going to be a wave equation with source. So it's going to be equal to the source. Okay, so we're going to impose this relation on all these variables. And again, there's going to be a notion of positivity. We're going to ask if the source is positive. So it's a lattice wave equation with a positive source. Now let's look at some examples. Let's say I look at the simplest case of 4-particle scattering. So this would be my entire picture. I only have one mesh. So I'd write down x13 plus x24 minus x23. This is 0, remember, minus x14, that's 0, is equal to a constant. And I have to demand that x13 and x24 are both positive. Well, I can use this type equation to solve for x24. It's just c minus x13. So if I plot things in x13 space, x13 has got to be positive, but it's also got to be less than c. So this space is the inside of this little interval. Let's go to the next example. 5 points. Okay, now these are all the points on the inside. Again, we just take, we imagine taking all the points on this past boundary of this null region and shooting light rays out into this kinematic spacetime and just filling out the rest, getting these meshes. So now we have 3 relations. We write down the relation for this mesh, and this mesh. Remember, we're demanding that all the x's are positive, but this is going to allow us to solve for all of these other x's, let's say 2, 4, 2, 5, and 3, 5, in terms of 1, 3, and 1, 4. So that's going to give us 5 inequalities, right? In x13, x14 space now, we have to have that x13 is positive, x14 is positive, but also that x24, 25, and 35 are positive. And these are some linear equations. I solved for 2, 4, 2, 5, and 3, 5 in terms of 1, 3, and 1, 4. And if you work it out, you discover this interesting pentagon. And if you go to the next example, it's a 3-dimensional shape. And amazingly, you get the 3-dimensional associahedra. So this is actually now a question we asked in kinematic space. Now you can complain, why do we know to ask this question? Why do we know about the wave equation? Why do we know about all the rest of it? That's where the vignette aspect of this story is. So there are sort of deeper reasons why we're forced to do those things. But it's just to give you an idea that in this simple kinematic space, there's a simple question you ask where the notion of positivity makes an important appearance. And the answer to this question reveals these interesting objects that are capturing everything about both the fact that the structure of poles is polytopal, as well as the fact that, that it factorizes on the boundaries. In fact, that's just what I'm saying here. The positivity tells us that the polytope correctly captures locality. Why does it do that? Because if I take 2 points, ij and kl, that correspond to chords that cross, we can trivially see that I can't set them both to 0 at the same time. In other words, they correspond to facets of the polytope that can never meet. Okay? They're kept apart from each other. And why is that? It's a simple consequence of positivity. Remember, I had this simple wave equation fact that generalizes for any points not necessarily close to each other as a Gauss's law fact, which is that x past plus x future minus x left minus x right is a constant, which is the sort of total charge inside this diamond, which is positive. And so if I put x past to 0, I can't also put x future to 0, because then both the positive terms here would be 0, and I'd have the sum of 2 negative terms equals something positive, which is impossible. Okay? So just positivity enforces locality, what the series of poles is that can come together. And I don't have time to explain it in detail, but this also explains factorization. Okay? There's a sort of a one-line argument for what happens if you put a given x to 0. That when you put that x to 0, you see that the set of the set of inequalities, the set of these mesh relations that we had talked about, factorizes into the product of 2 independent set of relations for 2 different triangles, which is exactly giving you the direct product at the level of the actual polytopes, giving you the direct product of the corresponding. Okay, so again, in the spirit of the vignette, I have not had time to. I've just had time to tell you about what the shape is, but just to say very quickly, what is the amplitude in this picture? The amplitude is actually begins life is fundamentally determined not by a function but by a certain differential form. It's a differential form that lives in this kinematic space, which has the properties, but is completely determined by this shape. And it's completely determined by the shape, by the property that it has a prescribed form of logarithmic singularities on the boundaries of all the facets. Logarithmic means that in some local set of coordinates, it looks like the wedge product of a bunch of d logs. If you have an n-dimensional space, there's some set of coordinates where locally it looks like the wedge product of d log x1 up to d log x. It turns out that asking that completely determined, once you give the shape, asking for a form to have this property that has logarithmic singularities on and only on the boundaries of the shape completely determines what the form is, thereby completely determines what the amplitude is. And so the fact that the shape factorizes on its boundaries is then just ported into the fact that the amplitude factorizes on its poles, which was what we ultimately wanted. Now, how do you compute these canonical forms? Well, one way of computing them is to take your shape and break it into simple ones and add up the canonical forms for the simple pieces. So that's like triangulation. So you can take these geometries and triangulate them. Well, there's one very natural class of triangulations of these polytopes that actually correspond to Feynman diagrams. They're associated with taking every vertex, drawing a certain simplex that comes out of every vertex, and using them to triangulate the whole shape in a slightly interesting way. But it's a sort of universal way of triangulating large classes of polytopes that when you apply to this polytope gives you Feynman diagrams. Okay? But it's not the only one. There are many other triangulations as well. Other ones tend to be much more efficient. They give you shorter formulas than with Feynman diagrams. But more important than that, the fact that the amplitudes are associated with this polytope manifests a certain hidden symmetry that these forms have. It's something that we've called projective invariance. And interestingly, the Feynman diagrams piece by piece violated. So you don't see the symmetry in every Feynman diagram separately, but it's the symmetry of the entire object when you add everything up together. Okay, so as I said, there are other triangulations that are possible. I'm not showing you any of these things, but this is but they're sort of beefier in the sense that they're really new expressions, even for these very simple objects that are associated with these geometries that manifest hidden facts about even these very stupid seeming theories. And there are other methods to get the form without triangulation, and that is something that I'll come to. All right, so everything that I told you about was just for the story of tree amplitudes. Now, if you think about general amplitudes that have loops and more in complete generality, what we're talking about here is the theory of n by n matrix valued spin zero particles. And so we've known since the 70s that we should think about the amplitudes or correlation functions for this theory in a large n expansion, and that we should group together the Feynman diagrams that can be drawn on surfaces with particular genus and boundary structure with marked points corresponding to external particles. So tree amplitudes correspond to, in this picture, correspond to disks. So you draw a disk with n marked points on the outside. But a loop amplitude, for example, the simplest loop amplitude would just be a disk with a little hole on the inside. Double trace contribution to the amplitude would be an annulus. So you'd have a bunch of points on the outside as well as a bunch of points on the inside hole, and so on. Okay, what we've been figuring out over the past couple of years is how the story that I just told you at tree level actually extends to all surfaces. And we claim that there is this interesting polytopal structure associated with any reading surface, any two-dimensional surface. Now, it turns out to be much richer than the story we just saw for the disk. As with the disk, there's a facet of this object, of this polytope, that corresponds to every homotopy class of arcs that you can draw on the surface. Now, already, this is interesting, beginning with the case of even the annulus, because there are infinitely many of these arcs. Okay? You imagine you have an outside circle and an inside circle. You can draw arcs that wind around the inside circle any number of times. So this infinity is really what we've been struggling with to understand what is going on. And so that means that these polytopes that we're talking about are generally infinite. They have infinitely many facets, and they have an interesting fractal structure that reflects the infinity on the surface. Okay, but nonetheless, what do these faces capture? Just like we saw for the case of the disk, the point was that if you take any arc on the surface and you imagine that you pinch it, that's where the factorization came from, right? We drew this sort of arc on the surface and we pinched it, and that's how we got the product of two arcs. Well, that analog of pinching exists for any surface, and you can pinch on any arc. And what you get is simpler surfaces. Sometimes they're products, sometimes they cut and they open up. There's various things that they could do. I've given you a couple of examples here. Sometimes if you have a closed loop in the surface, they do something even more interesting. So, for example, if I pinch this closed loop on the surface, then I get the product of a disk here with a puncture that corresponds to having pinched that delta closed line on one side and the other, and so on. Okay. So the claim is that there is in fact a polytope for every surface that captures everything about the correct notion of factorization for the surfaces as you pinch any arc. To begin with, one naturally associates the arcs that go between boundary points with propagators in Feynman diagrams. And there's no obvious home for these guys that are closed loops that have nothing to do with that. However, it turns out they're a necessary part of the story, okay? that you cannot build sort of closed polytopes without them. And these are the sort of polytopal avatar of something that we're familiar with in string theory, that closed strings are inevitable even if you start with a theory that only has open strings. And again, just in the spirit of the vignette, I'm just showing you what some of these things look like. Okay, so here's the surfacehedron we just saw for this example, 6-point scattering. Here's the surfacehedron for a one-loop example, a sphere with 3 punctures. And so these are all kind of normal-looking polytopes. If we had longer, we could go through and stare at all the faces and see how every arc you draw on the surface cuts it open in some way that's reflected correctly in the facet structure these interesting objects. But then things start getting interesting when you have an annulus, like this example. And I don't know if you can see it here, but this is already something that has infinitely many facets. You see they're getting skinnier and skinnier and skinnier, and they're asymptoting to this interesting sort of hexagon that's sitting there in the middle. All of these infinitely many facets are associated with the curves that wind around the surface more and more and more and more and more. And this guy that they asymptote to is associated with that closed curve that goes around the outside. As you see, we cannot get rid of it, even if whether we want it or not, it's sort of forced on us in order for the polytope not to have a hole in it. And again, as I mentioned, in general, there's an even more interesting fractal structure. You start seeing it already in the case of the simple example of a torus with a puncture, where I really have zero time to explain what this picture means. But here, as you can imagine, there's now infinitely many curves that are labeled by a P and a Q, depending on how often you go around the two cycles. That means that there's a facet associated with this polytope for every rational number that looks like P over Q in lowest terms. And the way it manages to do that is that it looks something like this. Okay? So it looks like something where if we zoom in on every corner here, you see this actually cut out by another line and another line. And a projection of this picture down to 2 dimensions shows again the sort of interesting fractal structure as you zoom in. Okay, so all right, so that's the second vignette. I'll go quickly through the.
Can I quickly ask you a question before you move on?
Right.
You make this all sound like very unique, but at some level there needs to be like the dynamical details of what theory actually study, like what representation of the gauge group, what's the gauge group.
What went in here is that it was just a theory of scalars. It's just trace by cube. You can think of it as just trace by cube theory, literally for this. Now, there is an aspect of it which is actually, so literally trace by cube, the amplitude would just look like 1 over the product of 1 over the propaganda, just ones everywhere, okay? More general theories will have interesting numerators. They'll have some, and that's where the choice, is it gluons, is it something else, would actually come into what those numerators are. However, so this is literally just the trace by cube theory. But the point is that that pole structure is completely universal for any theory like this. And so the fact that the pole structure is polytopical and has all these properties really has nothing. Really is a feature of large N. And,
so in your language,
sorry, not even large N, just of the 1 over N expansion and nothing else.
The geometry would be going to many theories.
We could talk about this in more detail, maybe offline. But at 0th order, the geometry captures something about the poles. And so you could ask whether with exactly the same kind of geometry, is there a different kind of form that I can associate with geometry that doesn't only have these simple sort of d-log singularities on the facets, but has more interesting allowed singularities. And that would be one way to try to make more interesting theories. People have found over the past few years that actually higher things like phi to the 4 theory, phi to the p theory sort of live inside these objects in interesting ways. Okay, so but it's less trivial than what I was. Oh, sorry, it was less sort of obvious than what I was just telling. But the general statement is that the sort of pole structure is indeed universal and is it just depends on there being some n, not even large n, but it's a 1 over n expansion for some adjoint colored field, some adjoint colored field. All right, I think I am out of time. Can I maybe have 5 minutes, Nanti? All right, so maybe I'll just say something. I'll just say something quickly about this second part. Again, in the spirit of a vignette. So let's go back to our very simple example where we had talked about the variables associated with the tree amplitudes. Remember, these were chords, xij, and we associated with this shape, okay, this interesting pentagon. Notice that the linear inequalities here on this pentagon capture the combinatorics and the compatibility of factorization. That was its entire point, right? That we managed to capture who can go with who by this shape, and that we cut out the shape by a bunch of inequalities. Now that's quite nice, but the shape is still not unique. Okay? By the way, it always has these interesting parallel sides and so on, okay? But it's still not unique. I can move those constants around, but there's still some sort of moduli associated with this shape. Wouldn't it be nice if there was some geometric way of capturing exactly the same information in a totally rigid way? Okay. Well, there is, and this is what it looks like. In this example, and by the way, these equations have been known since the 1960s, that they actually arose in the very, very early dual resonance model, in the dual model literature, were forgotten. They were rediscovered by Francis Brown around 10 or 15 years ago. We've taken them as an inspiration to try to go further. But let me try to explain what's going on. So here's what you do. I'm going to write down the following set of equations. Okay? So with every chord, instead of associating this variable x and writing down nonlinear inequalities, I'm going to associate a variable u, and I'm going to write down the following equations. U for ij, plus the product of the u for all the chords kl that cross ij is equal to 1. Okay? Now, first of all, naively, if I do that, I have n equations and n unknowns. And so naively, it would just have solution at a bunch of points, maybe. However, remarkably, it actually gives you a variety. Okay? It gives you a variety of the correct dimensionality. Okay? So in the case of the square or the pentagon or the more interesting n equals 6 object, we had 1 and 2 and 3-dimensional objects. Well, this set of equations would give us a 1, 2, 3-dimensional space. Okay? So they're the variety of the correct dimension. And once again, we say the word positivity here. We say that we want these u's to be positive. And here is where the word binary makes an appearance. Okay? Because if we ask that these u's are positive, notice that these equations tell me that the u's also have to be smaller than 1. Right? The sum of two positive things adds up to 1. So if this is positive, if they're all positive, they all also have to be less than 1. Okay, so these u's are variables that go between 0 and 1, but they have the following beautiful property, that if I set a u for a given chord ij to 0, right, that was the analog of what we did here before, when we set the x to 0. The boundaries before when we set the x's to 0. Here, instead, if I set these variables u to 0, then all of the incompatible chords by this equation must go to 1. Okay? Because I have to have the product of it. This is 0, so I have a product of a bunch of things that's got to equal 1. They're all less than or equal to 1, so they all have to equal 1. So the remarkable thing is that these very nonlinear equations have a consistent space of solutions. And in that consistent space of solutions of the correct dimensionality, asking the u's to be positive actually gives us a binary realization of exactly what we got a polytopal realization for before. Okay? So in other words, if I set a given u to 0, all the incompatible ones go to 1, not far away somewhere. They just go to 1 and to some sort of totally locked place. Okay, so, and now this is the part that you can go away and play with yourself if you want to have some fun over tea, is you can try to solve these equations in the case of the pentagon. Okay, you can just do it on in a few lines. And the most obvious thing you can do is to try to intelligently solve for the, for example, for 5 points, I'd write down this equation, and it's 4 cyclic partners, so 5 equations, and you can show that you can solve for all the u's, let's say in terms of u13 and u14. So you can do that. You can have some fun doing that over tea. But more generally, it turns out that that there are nice representations of solutions to these equations that involve auxiliary objects. For example, for this problem, even though, see here, that there is no real picture of a surface here with a metric or anything. This is a totally abstract picture that's just about compatibility and nothing else. But there's a realization of a solution of these guys that involves thinking about hyperbolic geometry inside that disk. Okay, so now you imagine that we have a space of uniform negative curvature inside that disk. Now all of these edges, 1, 2, 2, 3, 4, everything is a geodesic. And so all of these arcs are associated naturally with curves on the surface. I can do a conformal transformation to draw it as points ordered on the line, and the inside of this curvy pentagon is now that region of the upper half plane. And all the U's turn out to be very simple cross ratios of the points in the problem. Okay. So this gives a connection between solutions of the U equations and hyperbolic geometry and the worldsheet. Okay. So this is now something now very familiar to thinking about ordered points on a line for tree amplitudes is completely standard for thinking about the open string worldsheet. But this is just one representation of the solutions to these binary equations. And there are others. Okay, so here's another one. Okay, so here's another one where the solutions are given as ratios of very simple looking polynomials. Okay. This one is actually nicer in some senses because in this representation, you have to sort of by hand say that Z2 is bigger than Z1 is less than Z3. You have to give the ordering by hand. Here, so long as these variables Y are positive, Y1 and Y2 are positive, then all the U's, they satisfy the equations and they put the U to be positive and less than 1. Okay, so the Y's between 0 and infinity guarantee that we're in the sort of binary region for the U's. And this set of polynomials that makes an appearance, this is what's deeply related to cluster algebras and Quiver representation theory. Again, I have no time to tell you what that is, but these polynomials are known as F polynomials, and they have a completely separate purpose in life that has nothing to do with hyperbolic geometry, nothing to do with this picture of the worldsheet, a totally different set of purposes in life. Now, this binary geometry turns out to be intimately connected to the polytopes that we talked about before. Okay, so that's, and there's a feature of the polytopes that is telling you that there is a connection to the binary geometry, which if we go back to this interesting picture of the pentagon that we got, we can actually think of this pentagon as the sum in a precise sense, known as the Minkowski sum. It just means you take every vector in this space and you add it to every vector in that space. That's what the plus sign means. Okay? But it's not maybe so obvious ahead of time, but this interesting pentagon is actually the sum of 3 simple pieces. The 3 simple pieces are like 2 intervals in this little triangle. And this is literally the sort of polytopal version of the idea of a Green's function. Remember I told you that we're doing something like solving a wave equation here. Well, when you solve a wave equation with a source, it's convenient to solve for the Green's function, where you put the source just in one spot to be non-zero and then 0 everywhere else. Well, these simple pieces are what the polytope would look like if we only turned on the source in one of the meshes and not the others. So this is a non-trivial fact that these polytopes are naturally built out of simple pieces. And the simple pieces in turn, if you give me this interval, this triangle, and that interval, it's very natural to record the information about these guys with polynomials. And the polynomials are such that the integer vectors here are just the exponents that occur in the polynomial. So these are called Newton polytopes of Newton polynomials. And you see that these are precisely the polynomials that showed up in these expressions for the U's. And when you understand things more deeply, once you know what the polynomials are, probably once you know how the surfacehedron is built out of a simple Minkowski sum of pieces, then you know how to build these solutions. And finally, once we have these interesting variables that go from 0 to 1 and give us this binary realization of compatibility, then there's the following interesting object that we can build. It's an interesting integral. Okay, so we do an integral. It's sort of motivated by the Euler beta function. We do an integral over these positive coordinates. Remember, I told you these coordinates y1, that these y's, when they go from 0 to infinity, they guarantee that the u's are between 0 and 1. So we integrate over a simple form that has singularities on the boundaries of this space. So just like a d log y1 up to d log yn. If I just did this integral, I would get something divergent. So I regulate it by just taking the product over all the chords on the surface, the u variable that goes along with the chord to some power, to the power of the x that I would associate with that chord. That literally the x variable that we talked about even in our tree level example. Okay, so this needs a new variable, alpha prime, that has units of length. So this is interpreted as a string length, and the field theory limit is as usual as this string length alpha prime goes to 0. Now here's why this integral interesting. Remember, I told you that this integral would diverge if I didn't have these powers. So that means that as I take one of these powers to 0, let's say given x to 0, then I'm going to have a divergence. But the divergence is going to come from the region where the u's for the corresponding x goes to 0. So if I want to see what the coefficient of that divergence is, I go to that locus, that neighborhood. That u is going to 0, but then crucially, all of the incompatible u's are going to 1. Because they're going to 1, all of the variables that are associated with them completely drop out of this integral. And what I get is the product of two smaller integrals of exactly the same type. But now this is not only true when alpha prime goes to 0, but it's true at general alpha prime. Okay? So this ports this fact about factorization on massless poles to something that continues to be true at finite alpha prime, thanks to this binary property. That's the magic of this binary property. And so, for example, if I take the most trivial case of 4 points, where my u equations are just that u13 plus u24 is equal to 1, and the obvious positive parameterization of u13 and u24 would just be y over 1 plus y and 1 over 1 plus y that add up to 1. Well, if I plug it into this into the general expression that I told you, this is exactly the Euler beta function that we can also interpret here as the quote-unquote Veneziano amplitude, familiar from tree amplitudes in string theory. And again, as alpha prime goes to 0, it reproduces the field theory limit that we talked about before. But more generally, what's going on is that these y's, remember, are positive. They go from 0 to infinity. It's natural to parameterize them in terms of some e to the t. So these t's now run over all of space. And now what's going on is that the u's, this is now the case of n equals 5 point scattering. So I have a two-dimensional space. But as I go off into different regions in this two-dimensional space, different monomials in u, in these expressions for u, different monomials will dominate in different regions of this space. And so the space of y's, or its logarithm, the space of t's, gets divided up into regions with different, and in each region, the u's become effectively linearized. For example, in this region, u13 and u14 just go to y1 and y2, which turn into these exponentials. And then the integral that I talked about, the interesting part of the integral that I talked about, precisely becomes what we recognize as field theorists as Schwinger parameterization for the corresponding propagators. But you see, so in this region, the binary structure tells me that these u's are going close to 0 and all the other u's are going to 1. Because all the other u's are going to 1, if I interpret u's as Schwinger parameters, as exponentials of Schwinger parameters in this way, the Schwinger parameters associated with the other propagators are gone, and I only get the ones associated with this diagram. So in this way, every region, every asymptotic region is divided up into things that correspond to different diagrams. But there's one united object, which is summing them all together. Okay? So that's, we're not summing separately the different diagrams. We have one set of u variables, and the magic of the binary property means that asymptotically, in any region where only some of the u's are turned on, and the complementary ones go to 1, this integral turns into Schwinger parameterization in that region and gives us the field theory answer from the asymptotics. That's what guarantees that as alpha prime goes to 0, this turns into field theory, but it's not field theory. It has a non-zero alpha prime. And in these simple cases of just tree amplitudes, these are literally the string amplitudes at tree level. Okay. All right, so that's the story of the binary geometries, and I won't say anything about this in detail. I'll just end. But again, just to say that this is now what we've been largely thinking about for the past 6 months, is to find the analog. So there are these polytopes associated with any surface that capture in this linear polytopal way everything about the cutting of the surface. Well, we've been finding this binary realization for all the surfaces as well. And the structure of the u equations is that for all the curves on the surface, again, there's a variable u, and you write down u of x plus the product over y of u for all the other y's. Some integer that depends on x and y is the exponent. And who is that exponent? It just counts the number of times the curves x and y intersect each other. Okay, so in the simplest case of the disk, they could either intersect 0 times or 1 time, and that's what we got for the exponents, where it's sort of 0 if they're compatible and 1 if they're incompatible. And this generalizes in a nice way for all surfaces. All right. Okay, so let me precisely how this connects to string amplitude is something that we're still in the middle of understanding. I'll just say this very quickly, is that in playing with these equations, we originally ran into what you can think of as a minimal version of these binary geometries. Minimal in the sense that the only curves on the surface that we talked about were ones that did not intersect themselves. And already with those minimal versions, we could write down these integrals and we had objects that had all these sort of stringy properties that unified all the diagrams together in one object. They're ultraviolet finite, they're exponentially soft at high energies, but they looked much simpler when we, starting at one loop. At tree level, they're standard string amplitudes. At one loop, they look much simpler than conventional textbook presentations of string amplitudes. And more recently, just in the past month or so, we've discovered that this story sits inside a maximal story, where we really have to think about every possible curve on the surface, including the ones that intersect themselves. And when we talk about those guys, now these integrals now have these large infinite products, and at least at one loop where we've been understanding what is happening in some detail, these large infinite products give us the objects that we're used to seeing in real string amplitudes at one loop. The interesting Jacobi theta functions and so on, the kind of object you're used to seeing in string theory at one loop shows up here in this maximal version. But it's interesting that it's possible to sort of interpolate between this maximal version to a minimal one. We don't know if these things have any reasonable physical interpretation. As alpha prime goes to 0, they certainly reduce to ordinary field theory amplitudes. The maximal ones seem to be a different way of thinking about perhaps real string amplitudes, appropriately dressed up in some way to deal with the fact that we should not be talking about these dumb scalars, but talking about gluons and gravitons. It's likely these baby string amplitudes have some physical sickness. They might not be unitary, for example, at finite alpha prime. But anyway, this is still something that we'd like to understand and explore more. What's the purpose of life? Anyway, let me just end. So I think over the past decade, we've been seeing concrete examples where the rules of locality and unitarity, the rules of space-time and quantum mechanics, in the context of scattering processes, emerge from more elementary mathematical rubric. There is a common theme between the story of the amplituhedron that I didn't talk about here at all today, but I talked about in the last meeting to this group, and the surfacehedra that I talked about today. The common ingredients are some notions of positivity and topology in the kinematic space. And this very minimal amount of structure seems to be enough to breathe sort of physics life into seemingly very austere and empty territory. Of course, we're still looking for the general principles, but there are clues that the amplituhedra and surfacehedra are connected to each other. And I mentioned one of them in my response to Andreas's question. Surfacehedra have something to do with, are capturing the factorization structure that's sort of universal in any theory, at least any theory with colored parts. Including scalar theories, which is what we're talking about. And we've seen that there's a polytopal version of these guys and there's a curvy version of them. But the story of the amplituhedron for gluons is already curvy by itself. These are sort of nonlinear generalizations of polytopes into Grassmannians. And the reason for the curviness is that they also capture another kind of singularity that's not there in generic theories, but is there in Yang-Mills theory, which are soft limits. So amplituhedra their boundary structure is captured again for any theory, for any theory of gluons in the plane of limit. There is something non-trivial about the combinatorics of the boundary structure of all the possible singularities, and those are captured by amplituhedra. Now, obviously, this set of singularities lives inside that set. And so people have been finding sort of concrete ways in which at least the associahedra live inside the amplituhedron for tree amplitudes. In some sense, live inside. Clearly, this is a far richer object than that is. And I think over the past year or so, there's also very interesting hints of a connection between the sort of curvy version of the simplest versions of the associahedra and the simplest version of amplitude as well. And these connections are very mysterious from a physical point of view, but they're definitely there mathematically, and it's something to think about more. All right, thank you very much.
Are there any questions for Nima?
Maybe a very naive question, because you briefly mentioned quivers. If you look at the picture of your associahedron, that's for what, 6 particle exchange. This looks identical to, I guess, in that language, maybe you didn't have time to talk about it, to the exchange diagram for cluster algebra of type A3, I guess.
Yes, that's right, exactly. Yes.
So
in this case, yeah. So this is.
I was just asking if these were the quivers.
I did not say the word cluster algebra a little bit deliberately. Although I said it at some point. But indeed, at tree level, these things are cluster polytopes. They're polytope associated, exactly what you said. And the sort of first thought is that we should sort of continue. And there are cluster algebras associated with any surface. And even at one loop, there's a relatively simple finite cluster algebra that we could talk about. And back in 2019, this was our sort of entry into thinking about the more general story, is to say that those are the sort of polytopes we could talk about at one loop. And then in general, when you go to general surfaces, the cluster algebras are infinite, and there's all sorts of sort of mysteries about how to think about that. Well, a part of our voyage has been to discover that the cluster is not the right object, not quite the right object. It's close, but it's not quite the right object. And anyway, there are lots of clues lying around all over the place. There's not like the right object, but in this business, you cannot be slightly off. See, the reason you can't be slightly off is that in the end, everything is determined by sort of roughly factorizing to simple objects. So you have to have it exactly correct all the way down to the very simplest objects at the very, very bottom. And there are some little exceptions and little funny things about how standard cluster structure deals with this, which is not quite right. So these stories are not directly, very close, but they're not directly related to a cluster.
No more questions. Let's thank Nima again for a very inspiring talk.